This is a tutorial to implement the AcceptReject method for the demand process generator for the Cafe Java example. Last time we left off after creating a inverse transform method generator to generate demands for coffee, none, small, medium, large, following some observed frequencies of those orders being made. This time we're going to simply create a second generation method using the AcceptReject method and compare the two results in a bar chart here. First thing I'm going to do is from this existing code is make some slight changes. I'm going to adjust the name of our IVT process generator to append the IVT label. And since I changed the function name here, you can also see now that there's this yellow highlighted generate demand down below. You can actually see that there's an error in Spider seeing that we have an undefined name for generate demand. So we just have to update that name as well. The other thing I'm going to change is the samples that we generated from the IVT method. I'm going to also append an underscore IVT to the end of the samples variable. And you'll notice there's a couple of locations where that has to be updated in the later code as well. And finally, I'm just going to change the label on our plot to identify that these were generated using the IVT method. Okay, and let's add in a legend as well. Okay. So what we want to do now is to add in an alternative method for generating these demands using the AcceptReject method. And in this case, we're going to define a separate function right after the IVT method to generate demand using ARM, AcceptReject method. Now in this case, we have to take a slightly different approach to our sampling. The first thing we want to do is to choose one of these four options at random. So what we really want to do is to first make an array of alternatives. So similar to a cumulative distribution function for the IVT method, I'm going to create an array of alternatives with the cumulative frequency or the cumulative probability of choosing one of these four at random. It's essentially a uniform distribution with four options. So the probability of choosing the first, which would be none, no coffee, is 0.25, followed by 0.5, 0.75, and finally 1.0. So there's a 25% chance of choosing any one of these four alternatives. Now with the AcceptReject method, we are going to repeat a possible rejection process many times before finding one alternative that meets certain criteria. And that ultimate selection we're going to store in a variable called accepted, which I'm going to initialize it to be -1. What this means in my code is that if accepted is -1, it means that we've not assigned a valid demand, which again have these values of 0, 1, 2, or 3. And it means that we have to continue running our method. So the main body of this AcceptReject method is going to use a while loop. And it will continuously loop over this code as long as the accepted value is less than 0. So as long as accepted is -1, we'll continue trying to sample and find an adequate option. Now inside of this body is where we do the heart of the AcceptReject method. And this requires two random variables, R1, which I'm going to choose to be numpy.random.rand, and R2, which is numpy.random.rand. Now in the AcceptReject method, what we first want to do is to choose one of these four alternatives at random. And to do that, we're going to use this random1 variable in the same fashion as IVT. So we'll check, for example, if this random variable 1 is less than or equal to the 0 index of alternatives, so 0.25, alternatives index 0. I'm just going to include some filler code using passes right now until we finish this section. If it's not less than index 0 of alternatives, I want to run an else if check to see if R1 is less than or equal to alternatives index 1, and then we'll run some code. Else if R1 is less than or equal to alternatives 2. We'll run some code. And finally, if it's not less than 0.75, we know it's going to be less than that's going to be less than 1. So we can just have this else condition. All right, so for each of these options, we want to, oops, looks like I missed an equal sign here. That's what that error message was indicating, that yellow underline. Okay. So within each of these options, we want to perform the AcceptReject test. And we're going to be using the second random variable that was generated to perform that task. And in each of these cases, we want to check to see if the random variable 2 is less than or equal to the probability mass function value corresponding to this current alternative that we're looking at. So for alternative number 0, means we want to look at the entry 0 for the probability mass function. That's the probability of choosing no coffee. If indeed the second random variable is less than this value, which is about 0.16, then we can accept that demand alternative, which is number 0 in this case, and it will finish accepted equals 0, and it will, the next time it goes to check if this while will continue, it'll see that, okay, accepted is no longer less than 0, and it will continue on with the rest of the function. We can follow a similar process for these other cases. I'm just going to copy and paste code. So if in the second case, if the random variable is less than or equal to the probability that anyone chooses small coffee, then we'll say that the small coffee has been accepted. In the third case, we want to see if the random variable is less than the probability that someone would choose a medium coffee. And if that's true, then we'll say that the medium coffee was the accepted demand. And finally, in the last case, we want to check to see if that second random variable is less than the probability of demanding a large coffee, in which case that large coffee would be demanded. So after that, we're going to close out of this while loop. So make sure that we're on the same tab level as before. And the last statement is going to simply return whatever value was stored and accepted. So we know that it's something greater than 0 because it's broken out of this loop. So it'll take on a value of either 0, 1, 2, or 3. But we don't necessarily know how many times this loop is going to have to go to find an acceptable result. So we can run this script and just test it out in the console, generate demand arm, run it a few times, and it looks like we're getting a decent distribution of results. Haven't seen a 3 yet. Oh, there's 1. So it looks like we haven't miscoded anything so far, but let's create a plot to double check. So similar to before, we're going to make 1,000 samples using this process generator. I'm going to copy and paste our code to initialize samples for the arm method. So we're going to use the numpy 0 function with 1,000 samples. And then inside of this for loop, in addition to generating these demands to store in the IVT samples method, we're going to use a second line to store samples in the arm samples and just change the generator function from IVT to arm. So finally, we're going to also repeat this counts and fraction for the 2. So I'm going to just update these variables for IVT for counts, and then fraction for IVT, and update the other area where it highlights it in yellow down below. So I'm going to copy these 2 lines of code that were previously for IVT and just replace this suffix with arm, and making sure to fix all of the other references to from IVT to arm in the actual computation as well. Right. Arm, 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 arm. Looks good. Last thing is to adjust our plot. So I'm going to just copy and paste this instruction to create the bar plot, change it from fraction of IVT to fraction arm. And I think I'll also adjust the bar width here to 0.3 units. So 0.3 units, 0.3 units, 0.3 units for the bar width. Offset the IVT by 0.6, the bar width to 0.3, and also change the color to red. The other settings look pretty good. Let's rerun this file, and we can visualize some of the results. We see that, again, between the observed data, the IVT method, and the ARM method, the results in these four categories all look fairly consistent. And again, in a later lecture, we'll discuss a statistical test that we can run to actually quantify whether it's likely due to chance or some other factor, the differences that we observe between these different process generators.